My name is Andy Klump, and I am the president and founder of AshWare. We have been selling eTPU, CPU, multi-target simulators, compilers, training, consulting, literature, and other products since 1994. I'm proud to announce AshWare's upcoming MC33816 simulator and state machine coding tool and related products. Let's talk about the various simulation features of the AshWare simulator. There are three menus from which most of the simulation features can be accessed: the Step menu, the Run menu, and the Breakpoints menu. Some of these features can also be accessed from pop-up menus that appear when the right mouse button is clicked from within an editable file. These include Go to Cursor, Toggle Breakpoint, and Toggle Mixed Assembly. Toggle Mixed Assembly switches between the Mixed Assembly view and the Source-Only view. The IDE has two main modes: Edit mode and Simulation mode. Right now, the AshWare simulator is in Edit mode, which I can tell because of the keyboard image seen at the top of the IDE. Let's single-step the AshWare simulator a couple of times. This can be done by clicking either the Step Over or the Step Into buttons, the difference being that Step Over will not enter a function call. These can also be accessed from the Step menu. The hotkeys F7 and F8 can also be used. Two things happen on a successful step. The first is that the line of source code associated with the current program counter gets highlighted red. The second is that the IDE's mode image that used to be a keyboard is now a red stop sign indicating that a simulation is underway. Now that the IDE is in simulation mode, editing of source code or other files is no longer permitted. I can go back to Edit mode by clicking the Edit button, or from the Edit menu by selecting Enter Edit mode, or just by typing within a source code file and clicking the OK button within the warning dialog that pops up. Note that the IDE's mode indicator has now switched back to a keyboard. The AshWare simulator can be free run. From the Run menu, select Go, or just click this green light. This time the IDE mode image shows a pair of running feet indicating that the simulation is running. Wow, looks pretty fast. I wonder if it could keep up with Alberto Salazar. Let's stop the simulation by clicking the red light button. Let's add some breakpoints. I'm going to put one near the top of the file and another near the bottom. Although I can add them from the Breakpoints menu or using the pop-up menu, it is easiest to just click on the sidebar, which is just off to the left side of the editable portion of the source code file. Notice that within the left sidebar, the breakpoint appears as green dots and the current program counter line appears as a red arrow. I can toggle the breakpoint between off and on by clicking on it multiple times. Notice on the opposite side of the editable portion of the window, there is another representation of the breakpoints and current source code line. These are called markers. The location of the markers shows where, within the entire file, the breakpoints and current program counter line are located. I can quickly navigate to these lines by clicking on their markers. I know this is a bit of a non sequitur, but bear with me. I am going to search for the text AutoGen, which was created by the State Machine tool for each state, so it appears many times throughout the source code file. I can see that because of the many brown markers within the markers pane. Clicking on one scrolls it into view. Let's close the search dialog. Notice that the search markers remain. What happened to the debug markers, current program counter, breakpoints, and such? At the top of the markers pane is a little magnifying glass. Clicking on it toggles the markers pane between search results and debug results. Double-clicking on it reopens the search dialog. Let's close it back down. Now let's add a bookmark to this source code file and another bookmark to the vector file. I can switch between these two file locations using the GoToBookmark function. Okay, let's delete all the bookmarks and continue. Let's go to the peak off state within the source code file and take a look at the text autogen_peak_2_hold_state_epilogue. This is auto-generated by the State Machine coding tool and in source-only view looks a bit curious. Let's switch to mixed assembly view and see what is going on. Now the state's epilogue code can be seen. The epilogue consists of several assembly instructions that are preparing the state machine for the events that would transition the state machine to the next state. Let's run the AshWare simulator to a line of source code using the GoToCursor item within the pop-up menu. Now let's go to a line of assembly by starting from a line of disassembly instead of a source code line. Okay, now let's reset the simulator and close the state machine. Then let's click the Step State button. Since the state was stepped, the state machine automatically opens and the current state gets highlighted red, similar to how the current line of source code also gets highlighted red. Let's step the state machine a few more times until we get to the point where the state is bouncing between peak off and peak on. Notice that the last traversed transition also gets highlighted red. In this case, the occur transition is highlighted, which is the transition caused by the own current reaching the pre-programmed trip point. The return transition back to the peak on state is caused by the TC2 event. I'll translate. TC2 is an event that occurs when counter number 2 reaches its terminal count. Indeed, if we look at the source code in the peak off state, the first instruction is LDCD, which resets counter 2 and loads counter 2's terminal count register with a value from data RAM. So, as is typical with MC33816 code, a key task in this state is to prepare the event or events which will cause a transition to the next possible state or states. Lastly, let's close the script file and reset the AshWare simulator. Then, let's step a script by clicking the Step Script button. The script file is automatically opened and the current script line pops into view. In this case, the script command is set battery voltage, which is a script command that, not surprisingly, modifies the simulated battery voltage. I suppose we could have used the syntax SBV instead, but then we would have been assembly language architects, not simulator designers. If you think about it, the MC33816 is like a teenager who lacks self-motivation in the sense that there needs to be some configuration by a separate micro across the SPI bus for it to do anything at all. The script commands file performs those required tasks, plus does other important things like configuring the battery voltage, setting sense resistor resistances, etc. Let's say I want to simulate the alternator kicking in after 10 milliseconds and bringing the battery voltage up to 14.5 volts. Let's look at the bottom of the AshWare script commands file to see how this is accomplished. Let's do a go to cursor on the line right below the line of the wait time script command. The current line goes to this set battery voltage script command, but does not execute it right away. I can tell that because the current time listed in the status indicator at the bottom of the IDE indicates that the simulation is still near time 0. Now let's single step a script command. The set battery voltage script command executed at 10 milliseconds as indicated by the status indicator. Let's talk about the Ashware simulator's wait row table window. The wait row table window is viewed in the Ashware simulator by going to the View menu and selecting the Wait Table Rows window, which can now be seen at the right-hand side of the Ashware simulator. The micro has just been reset, so the table is uninitialized and none of the things to wait for have been specified. At the bottom of the screen in the Logic Analyzer window, the wait waveform can be seen. I'm going to run the Ashware simulator for about 20 microseconds so that several cycles of wait activity are visible. The typical event response nature of the 33816 can be seen. Basically, the core executes for a while and then hits a wait instruction. At the wait instruction, the core waits for the first of up to 5 different events to occur. But until one of those events actually occurs, the core just sits at the wait instruction waiting. But then one of those events actually does occur, and as a result, core execution continues until the next wait instruction is hit, at which time the core waits again for the next event. Now let's look at actual code executing. First, let's reset the Ashware simulator. Then, let's step a few instructions until the first CWEF instruction is hit. This is seen in the source code window at the red line of code, which is the line of code that is about to execute. The CWEF instruction has 3 arguments. The first argument is JR1, or Jump Register 1. The jump register contains a code address, which is the destination where the code will begin executing should this particular event actually occur. Since there could be up to 4 other events that could occur first, this path might not actually be the one that gets traversed. The second argument specifies the event to wait for. The event specified here is the start event. The start event is when the start pin, which is an input pin to the device, goes high. The third argument is the row number of the wait table. This must be one of the 5 rows in the wait table, and in this particular case, row 3 is being specified. Now let's execute the instruction and see what happens to the wait table. Row 3 in the wait table got filled by the just executed CWEF instruction. The second column is the destination address named boost. Boost is actually a code label in the code as seen in the source code window. The JR1 register must have contained the code address corresponding to this boost label when the CWF instruction was executed. I'm going to increase the size of the Logic Analyzer window so that the start signal, which is lurking just below the wait signal, can be seen. Since row 3 indicates that the event we are waiting for is this start pin to go high, when it does go high, the wait should end and more code should execute. And as I run the Ashware simulator a little forward, indeed I do see the start signal going high, and as a result, the wait ending and the code following the boost label actually executes. Now that first wait was fairly simple because there was just a single event being waited for. During the wait that is active at 5 microseconds, there are 2 active events being waited for. I can tell this because in the state column, I see that rows 1 and 5 are both on. Although the event in row 3 has been specified, because it is listed as off, this event, which is start pin high, will not cause the wait to end. The 2 events that are being waited for are own current high and start pin low. The start pin low is used to terminate the injection cycle, so right here at the very beginning of the injection cycle, we would not expect this event to occur. Each core has an associated current event sensor. The row 1 event that is being waited for here is for the peak current to be reached. Let's adjust the logic analyzer so that this signal can be seen. At about 7 microseconds, this current sensor trips. This indicates that the current reached the programming trip level, thereby causing the comparator's output to go high. As expected on this event, the wait cycle ends, thereby allowing the core to execute event handling code. Let's take a look at one last wait cycle at about 17.5 microseconds. In this case, the row 1 and row 3 events that are being waited for are both terminal count events. I'm going to further adjust the logic analyzer window so that the 3 terminal count events used in this code can be seen. Now, the way the counters work is they get reset and then free run until they reach the end count, at which time they stop and are said to have reached their terminal count. When used in the wait table, such as they are being used here, the reaching of the terminal count is an event that can cause code to execute. Let's zoom out the logic analyzer such that several thousand microseconds are visible, and then let's run the Ashware simulation. The peak-off counter is used during the peak portion of the injection cycle. In the middle of the injection cycle, the brief peak decay can be seen. This is a brief period between the peak and hold portions of the injection cycle when the injection current is allowed to decay from the higher peak level down to the lower hold level. During the latter half of the injection cycle, counter 1 is active. Note that this is the name of the counter given in the documentation. Unlike the other 2 counters, no more easily understood name has been assigned to this signal in the Ashware simulator. During almost the entire injection cycle, current 1 feedback comparator activity can be seen. This is because this example program uses the current sense comparator throughout the entire injection cycle to set the upper injection current limit. Let's take a look at the Ashware simulator's watch window. Let's open the watch window by going to the View menu and selecting Watch. The watch window appears at the bottom of the Ashware simulator. Several variables have already been entered for selection. I'm going to add one more by selecting it in the source code and dragging it into the watch window. All the variables initially have a value of 0. This is because they have been automatically initialized to 0 by the Ashware simulator at reset. Let's single step the simulator and see what happens. Notice that all the variables have magically gotten a new value. Actually, it wasn't magic. Initial values have been written by scripts in the script commands file. In the actual hardware, this initialization would be done by SPI commands. We could do that here too, but it is far easier to understand using actual script commands. Let's reset the Ashware simulator again, but this time let's single-step script commands instead of instructions. Here we are at the section of script commands that do the actual initialization of the data memory. As I step through each script command, I can see each variable change value. Now let's open up a memory window to see the data memory directly. The data window shows the data in hexadecimal format, while the default for the watch window is decimal. Let me configure the display to show the min current variable in hexadecimal instead. Now the value can be seen to match that of the memory window. Let's modify a variable's value by typing in the value column of the watch window. The value can be seen to change in both the memory window and the watch window. Let's open the Ashware proprietary vector file by double-clicking on the vector node in the project. The vector file has 2 main purposes. First, external pins and internal simulation nodes can be given more human-readable names. Second, complex waveforms can be driven onto groups of input pins. In this Ashware proprietary vector file, several such nodes have already been renamed, but there are no complex input pin driving waveforms. let's drive 4 start input pins with a complex waveform. But before we do that, let's take a look at how the start pin is being driven right now. In the script commands file, a series of write binary pin and wait time script commands generate pulses on the start 1 pin. Let's comment these out. Instead, let's use the vector file to drive in an infinite sequence of start pulses on 4 start pins: start 1, start 2, start 3, and start 4. There are already a number of node commands in the vector file. Let's add additional node commands for the missing start pins. Now let's add a group command. The group command is used to group simulation nodes so that they can be driven together. Let's make a group named Start Pin Group and add the 4 start pins to it. Now we need to specify what values 0, 1 to drive each of the input pins that are going to be driven using state commands. Since each group has 4 input pins, each state must have 4 zeros and 1s. The format is simple binary. The next needed command is the frequency command. This command establishes a master clock for the vector file. The units are megahertz, and this is typically left at 1 megahertz because this results in a 1 microsecond clock period, which I find to be intuitive and easy to remember. Plus, I am an expert at both multiplication and division by 1. Now we are at the main banana, which is the wave command. Following the wave command comes the name of the group whose input pins will be driven. This is followed by a series of states and clock counts. The first command is all off, and it is followed by the number 10. 10 is the number of master clocks to wait before continuing on to the next state. Since the master clock is set to 1 microsecond by the frequency command, there will be a 10 microsecond delay before the next state command is driven onto the input pins. Let's create a 1 millisecond positive pulse on the start 1 pin while keeping the other 3 start pins low. This is done by entering the name of the state 1 on followed by the number of master clocks. The same is done for states 3 on, 2 on, and 4 on. You are probably wondering about the parentheses. Parentheses are used to enclose a loop. Following the closed parentheses comes a loop count, in this case 2, which indicates how many times to run through the loop. Oh, and don't forget the end statement. This terminates the wave command. Note that multiple wave commands are supported. Okay, let's give it a whirl. Let's click the right mouse button inside the Logic Analyzer's waveform pane to cause the Ashware simulator to run to the point in time corresponding to the mouse location. Hopefully Jeff Miller hasn't put a zilch chord under my keyboard. Oops, typo. Let's fix it and attempt to run the Ashware simulator again. Looks good, but only the start 1 input pin is visible. Let's increase the size of the scope window and add all the start pin signals to the Logic Analyzer window. Let's zoom out and run the Ashware simulator a little further. It's kind of a bummer that only 2 pulses occur. It would be really nice if the waveform was continuous. Let's do that by changing the discrete loop iterator of 1 to be an asterisk. The asterisk signifies infinity. Voila, poetry in motion, not to mention lower emissions and better gas mileage. Almost forgot. It is always a good idea to measure things because things can look right but actually be wrong. Let's make the start 1 signal the active signal using the keyboard's up and down arrow keys. The active waveform is red. The start 1 pulse should be about 1 millisecond. Let's place the left vertical cursor on the start 1 pin's rising edge and the right vertical cursor on its falling edge. To get the cursor on the exact edge, snap to it using the keyboard's left or right arrow keys. Down here in the delta cursor box, I see that it is indeed 1 millisecond. Perfect. I expect the Ashware simulator to show 4 milliseconds between leading edges. The built-in make capability handles the building of the executable image file by examining the timestamps of the source code files to determine which compiles, assembles, and links, if any, are required. The key is that in many situations no code rebuild is required, and by skipping the build process, significant time can be saved. Although in these simple examples a build takes just a second or two, for big applications a complete build could take several minutes. The AshWare simulator supports two types of builds and makes, internal and external. This first example uses an internal built-in make, in which all assemble, compile, and link stages and all settings are controlled by the AshWare simulator. This is the most common way to use the AshWare simulator. They are used in the build. Let's open a source code file by double-clicking on it. Then let's make a small edit and close the file. Now let's single-step the simulator. Because the source code file timestamp is later than the timestamp of the executable image, a rebuild occurs. And because a build error occurred, the IDE stays in edit mode and the single-step request is ignored, as can be seen by the picture of the keyboard at the top of the IDE. Let's click on the error referenced in the output window. The source code file opens and the guilty line is highlighted and scrolled into view. Let's fix the error and run the AshWare simulator by right-clicking the mouse in the Logic Analyzer window. Voila! What nice waveforms. In the output window, I see that the build was successful and that the executable image was loaded into the target's code memory. A complete rebuild can always be forced by selecting Build All from the Build menu. Let's switch to a project that uses an external built-in make. This make.bat build batch file is called to build the code. It must be written such that it executes with a 0 exit code on success and a non-zero exit code on failure. This executable image file should be set to the file generated by the running of the build batch file. These files underneath the executable image file are automatically placed there by the AshWare simulator because they are all referenced within the executable image file. Let's single-step the simulator. The simulator runs to the first line of source code, then halts. In the output window, this line from the running of the build batch file indicates that the GNU make called by make.bat thinks that the build is up to date. Let's go back to edit mode by clicking on the Enter Edit Mode button. Then let's open one of the source code files by clicking on it. Let's modify the source code and close the file. Then let's step the simulator again. A build error occurred which caused the build batch file to return a non-zero exit code. The build batch output gets piped to the output window where the error is visible. Clicking on the error brings it into view. Let's fix the error and single-step the simulator. Success! The AshWare simulator executes a line of code and pops the just executed code into view. In the output window, I can see that this time the build actually occurred. Then, the executable image was reloaded into the target's code memory, and then the AshWare simulator was stepped. Let's talk about circuit windows. Circuit windows are opened within the AshWare simulator from the View menu by selecting the name of the desired circuit. Let's select the DC to DC converter circuit window, since this is the circuit that is being simulated in the AshWare demo. You will notice that there is a black box on the left-hand side of the circuit window that encloses the DACs, comparators, resistor divider network, and op-amp. All the elements within this black box represent elements of the simulation that are within the MC33816. Outside of this box, to the right actually, are the circuit elements that are external to the MC33816. These include the boost capacitor, inductor, sense resistor, etc. These are all part of the model of the circuitry that is external to the MC33816. This particular circuit is one of the standard circuits that gets installed as part of AshWare's MC33816 simulator. However, it is possible to develop your own external circuit models, and this will be discussed later in this video. For now, let's talk a little bit more about this DC to DC converter circuit that comes standard with the AshWare simulator. The circuit is instantiated from within the script commands file using the place DC to DC converter script command. Other settings are set using the script commands that follow. The first thing to note is the circuit element values are red. At the top is a listing of the DC to DC mode. Let's put breakpoints on the two STDCCTL instructions that control the mode. Then let's reset the AshWare simulator and hit Go. The AshWare simulation stops where the mode gets changed to async. Let's single step such that this instruction gets executed. Notice at the top of the circuit window that the mode has changed to asynchronous. Let's hit Go a second time. The simulation stops at the next instruction that changes the mode. Let's single step past it. Notice that the mode is now listed as synchronous. Let's hit the Go button a few more times. Notice that the voltage falls during the synchronous period and rises during the asynchronous portion. Indeed, I can see that during the synchronous portion, the LS7 output pin, which turns on the power FET, is off. I'll expand the logic analyzer so that the current sense resistor's current waveform can be seen. Let's make this waveform active by hitting the down arrow key on the keyboard until it is the red highlighted waveform. When I place a vertical cursor on the current, the exact value is listed in the left current indicator as 0.13 amps negative. This is because the current from the capacitor to ground is routed through this sense resistor. Let's see if the current listed in the current window matches the current listed at this point in time in the logic analyzer. Both are negative 130 milliamps and therefore match. Now let's examine the asynchronous portion of the waveform by running the AshWare simulator to partway through the asynchronous period. Let's bracket the asynchronous portion of the waveform with the left and right vertical cursors and then zoom the logic analyzer to view just the area by clicking on the Zoom to Cursors button. Notice that the current rises while the LS7 signal is a 1. This becomes obvious when the left and right vertical cursors are placed on the LS7's positive pulses beginning and end. With LS7 on, current flows from the battery through the inductor, through the power MOSFET, through the sense resistor to ground. The diode is off, thereby blocking the current from flowing through the power capacitor back through the driver. Energy is being added to the inductor during this period. As the current through the sense resistor increases, the voltage across the sense resistor also increases. This voltage is multiplied by the op amp and compared with the voltage programmed in DAC4L. When the voltage into the plus input of the CUR4L comparator hits the voltage programmed in the DAC, the CUR4L comparator trips. This inductor current, as measured by the sense resistor, has hit its maximum. When the CUR4L comparator trips, the LS7 signal turns off, which turns the power transistor off, thereby forcing the current through the inductor, through the diode, and into the boost capacitor. During this period, the energy that was just stored in the inductor is transferred to the V-boost capacitor. The capacitor's gain is the inductor's loss, which is why there is a rapid reduction in the current through the sense resistor during this period. Note that the current is taking an entirely different path to the sense resistor during this period. It travels instead through the diode and the boost capacitor to get to the sense resistor. I wonder if it cares. Many of the circuit element values can be changed. Let's increase the V-boost voltage by increasing the DAC boost value to 80 hexadecimal. Notice that this results in a longer boost phase and that the boost voltage increases to around 80 volts. Notice that another circuit element can be added by right-clicking the mouse in the circuit window. Let's add a second visualization of the battery voltage. Notice that the just added battery voltage visualization matches the pre-existing readout of the battery voltage. The circuit has not actually changed. All that has been done is to add a second visualization of the simulation element. In fact, what looks like a circuit is just a static picture, and an ugly one at that. That's because I am no artist. However, we did hire an artist here at AshWare and gave her the task of creating beautiful pictures for our circuits. Let's change to one. That is me and my son on top of 3,742 meter high Mount Adams, just a couple hours from AshWare's headquarters here in Oregon. Mount Rainier, Washington State's highest peak at 4,392 meters, is visible in the background. It says here Mount Rainier is 12.5 volts. Must be a bug. Let's try another image. Oh, that's me and John backcountry skiing high in the Wasatch, just outside of Salt Lake City. 2.5 amps? No way. I'd say more like 25, but hey, that artist sure does great work. To create your own circuits that can be simulated with the MC33816, you will need your own Windows compiler. The external circuit demo that gets installed with the AshWare MC33816 simulator builds under Microsoft Visual C, though other compilers can be used. Create a model of your external circuit in C or other supported language. Your model will link to the AshWare simulator as a DLL or via another supported method. The following interfaces are required by the AshWare simulation environment. The first interface is Connection Discovery. Inputs to your external circuit must be outputs from the MC33816, such as HS1 through HS5, LS1 through LS7, and so forth. Outputs from your external circuit must be inputs to the MC33816, such as start pin or current sense pin, and so forth. Next is the element discovery interface. This provides the AshWare simulator with a method for discovering the nodes that are internal to your circuit so that they can be available as elements in the circuit window and displayed as analog or digital nodes in the logic analyzer. Next is the debug interface. This allows node and element values to be updated in the circuit window and logic analyzer as the simulation progresses. It also allows values to be modified via drop-down menus, double-clicking, dialog boxes, and that sort of thing. Next is the reset interface. Although the reset interface seems like it is simple, it is particularly important that all internal states be properly initialized to provide repeatable simulation runs. There is nothing worse than a simulation not acting the same on every run except perhaps boiled spinach. Such problems are always a result of incomplete state reset. Next is the step interface. The model must respond to a step by advancing its internal state to the specified point in time. The model must return the time of the next requested step. The AshWare simulator may call the model before this requested time, but will not call it after. That is the complete set of interfaces required to support simulation, display and modification of elements and element values in circuit windows, and the logic analyzer, and interfacing via scripts in script command files.